Swayam Prabha. Digital India. Educated India.
So, hello students, this is Nitin Kumar. I am an assistant professor in the Department of Physics at IIT Bombay. So, today I am here to teach you the course which is called Thermal and Statistical Physics. So, this is a minor elective course which is offered to our undergraduate BTech students. Okay. So, like I said, the title of the course is Thermal and Statistical Physics. Okay, so, this is the title of the course. So, I will give you a brief summary of what this course is all about. So far, so basically the main goal of this course is to understand physical systems which are not consisting of few particles, but they are consisting of many particles, right. And the typical examples of such systems is known as matter, right. You must be familiar with many forms, like especially three phases of matter: gases, liquids and solids. And as you know, all these phases of matter, they consist of large number of molecules, typically of the order of 10 raised to the power 23. And I am assuming that so far you all of you must have done a basic course in mechanics or classical mechanics, where you apply Newton's equations of motion in order to predict the position and momentum of a particle at any later time given certain initial conditions, right. So, you might be tempted to basically apply the same approach when you are dealing with systems which we are calling matter, like typically 10 raised power 23 molecules. But as you can already imagine that working with 10 raised power 23 molecule is a daunting task, right. So, it actually becomes impossible to keep track of positions and velocities and momentum of all these particles. So, therefore, and it turns out, as we will learn in this course, that this approach not only becomes impossible, but also to certain extent is unnecessary, right. And basically in this course we will work out a formulation in order to deal with such systems and how to understand physical properties of these systems. All right. So, this in a nutshell is the basic underlying goal of this course. All right. So, maybe very briefly I will tell you what are the course contents going to be. So, course contents, right. So, basically conceptually this course is divided into three categories. So, the first part of this course is known as kinetic theory. The second part of this course is thermodynamics. And the third part of this course is known as statistical physics. Statistical physics. All right. And I will just give you very brief few sentences about all these subtopics that we are going to cover in this course. So, basically in kinetic theory, we will essentially do the same thing that I just told you about, which is impossible and unnecessary, right. So, we will basically apply the ideas of mechanics, classical mechanics on every individual molecule, right. So, basically so what we will do is we apply laws of mechanics on each molecule of matter. Okay. And maybe I can write here to understand physical properties of matter. So, that is what this course is all about, and we are always interested in matter, which is collection of many molecules. And you might ask, like, I am contradicting myself, because I just said that it is very difficult to keep track of every individual molecule, right. But it turns out when we deal with this kinetic theory, we make drastic assumptions, right. And and maybe I can write here under drastic assumptions, which we will talk about, right. It turns out when we make a certain set of assumptions, this problem actually becomes much easier to handle, but also there is a limitation, because then you are making these drastic approximations which are not really applicable to real matter per se. So, therefore, it has its own limitations, right. But still under those set of assumptions, we can still talk about various properties of matter, right. So, we can still understand the physical interpretation or implications of quantities like pressure, temperature, and many other emerging properties, as we will talk about in this course, all right. But as I said, it has its own limitations, right. So, so that is the first part of the course. So, in the second part, which I call thermodynamics, here what we will do is we will completely ignore the underlying microscopic details, right. So, ignore underlying microscopic dynamics or details, dynamics of molecules, right. So, this is completely opposite to what we did here, right. We just ignore them, but the very starting point of this subtopic is basically to start with macroscopic scopically measurable quantities like temperature and pressure and so on, right. So, this is how we deal, this is what the course of thermodynamics, like the subtopic of thermodynamics, is all about. But again, this has its own limitations. The biggest one, which will anyway discuss, is it is difficult to conceptually understand the concept of entropy. Okay. So, I will just write here, it has certain limitations, right, certain limitations, and in order to handle those limitations, we will move on to what is known as statistical mechanics. And the starting point of statistical mechanics is basically, I will just write one word, entropy, right. So, you start with entropy and derive all the physical properties of matter like temperature, pressure and so on, right, heat capacities and all those things, all right. And it turns out the formulation of statistical mechanics can be applied to all phases of matter, right. So, this is almost the complete theory that we have if we want to understand matter, all right. So, what we will do now is, so before we go into kinetic theory, I will just very quickly mention certain good textbooks which will be really useful for this course. So, books, right. So, I will just list down a few books which I usually follow to basically design this course, and which will also be useful if you want to like go home and read these topics in more detail, right. So, the first one being Concepts of Thermal Physics by two authors whose both last names are Blundell and Blundell, and the other one is Thermal Physics by Charles Kittle, all right. And another very good book is the book is Kinetic Theory, Thermodynamics, and Statistical Physics, by 3 authors, Garg, Ghosh and Bansal. All right. Another good book is Thermal Physics by Daniel Schroeder, SC. And for statistical mechanics, so this is another one, classical and statistical thermodynamics by Ashley Carter and for statistical mechanics there are other good books. K. Huang and Patharia and so on. Okay, and there are many more books which I am not really listing out, but this will give you a decent bit of material to basically go to read about. All right. Okay. So so let's start with the with our first subtopic of this course, which is kinetic theory. All right. So kinetic theory. Okay. And kinetic theory is basically built upon two basic postulates, right. So built or based on two fundamental postulates, fundamental postulates. So first one being that the matter consists of identical molecules, right. So matter consists of identical molecules which are large in number, right, of the order of 10 raised power 23 and so on, right. So we are dealing with very large numbers, right. And the second postulate is that the thermal energy causes molecular motion. So which basically means if you are at certain finite temperature, all these molecules, they are always moving, right. So there is certain thermal motion associated with all these molecules. All right. And before we really start, I think it's worthwhile to spend little bit time on maybe discussing what matter is, right. So what do we mean by the word matter? Okay. So basically what we can say is so classification of matters, classification of matter, right. So how do we classify matter, right. So most of you already know the matter has there are three phases of matter, like typically we talk about gases, liquids and solids, right. And now the question is, how can we classify these phases, right. And one way to do that is through what is known as energy, right. So total energy, right. So total energy of any system at any given point is basically sum of two parts. One is kinetic energy and other one is potential energy, right. So like I said, like in the second postulate of kinetic theory, the kinetic energy is basically a consequence of temperature, right. So, if you have certain temperature, all the molecules will be moving with certain velocities, and you can assign a kinetic energy to those molecules at any given temperature, right. And the other one is potential energy, which is basically how two molecules they are interacting with each other, right. So, you as we know, right, like the molecules, if they are charged particles, so they can attract or repel each other, right. So, due to these interaction energies, there are interaction forces acting on all these molecules, right. So, the kinetic energy is a consequence of temperature T, but on the other hand potential energy is due to the interaction due to two molecules interacting with each other, right. And for, like I said, for matter to exist, there must be a certain range over which this potential energy is negative, right, which would correspond to attractive forces, and typically the plot of potential energy looks something like this, right. And now so basically interaction forces, okay. So, based upon these two fundamental energies, we can now talk about matter, right. And so the case 1, can be when your kinetic energy is much greater than potential energy, right. And you can already imagine this will be true at very high temperatures, right. So, at high temperatures, okay. And in that case, since your kinetic energy is much greater than potential energy, so your total energy lies somewhere here, and therefore, your matter, the molecules in the matter, since they are moving so fast and the forces due to interaction potential are so tiny that these molecules do not care about it, and they continue to move, right. So, they continue to move in all directions, and as you can imagine, such a phase of matter would be a gas, right. Such a phase of matter would be a gas. Now, clearly we can now go on to the to basically case 2, right. So, case 2, and case 2 is where your kinetic energy now is much smaller than potential energy, right. And in that case, your total energy would lie somewhere here, right. In which case the two molecules, they are always bounded to each other between these two distances, right, which I can call R1 and R2, right. So, they are always bounded between these two distances with their certain equilibrium distance, which is R0, all right. And in this case, and when I say bounded, you know the typical examples of such a phase is basically known as a solid, right. So, where all the atoms or molecules, they are arranged in a certain periodic manner, they have certain distance between each other, right. And so, therefore, and of course, since kinetic energy is very low, this is possible only at low temperatures, and like I said, such a phase would be known as solid, right. So, I can in fact write here. So, this is a gas and this is a solid, right. And now you might ask what happened to liquids, right. So, I just completely skipped the liquids, and that is where it is actually a very interesting case. So, let us talk about that. Case 3 is when your kinetic energy is still greater than potential energy, right. But you so maybe I can write at intermediate temperatures, but on top of that you introduce confinement, right. Introduce confinement. What do I mean by that? So, say you have collection of these molecules, rather than they being free in the space, now they are confined in certain volume, right. So, what I mean by that is, so you have a box and you have these molecules which have kinetic energy greater than potential energy. So, there is no reason for them to stay in a solid phase, but it turns out under certain conditions and if you wait for long enough, these molecules they can condense into what is known as a liquid phase, right. So let me draw it. So what happens is what happens is after some time they condense into a liquid phase, which is like a condensed form of these molecules, right. So, and it goes everywhere, right. So, this is liquid. Okay. And let me spend little bit of time, because it's actually a very fundamental concept which I am coming on to, which is called pressure, right. So, the very act of confining a molecule. So, what happens? So, remember, like I said, these molecules, since they are at finite temperature, they are always moving and they are always making collisions with the walls of the container, right. So, they are always hitting the container here and getting reflected elastically from the container wall, and they are applying certain force on it, right. And that force will correspond to a certain force per unit area on all these walls. All these molecules will cause certain force per unit area, which is basically pressure, right. And if you do not apply any external force in order to stop in order to balance that forces by the molecules, the gas will the collection of these molecules will start expanding, right. So, therefore, we must apply certain external force per unit area in order to confine these molecules, right. So, therefore, maybe I can now conclude. So, the point that I am coming on to is, so in case 1 and 2, the only parameter that we were changing was temperature, right. So, what I can do is I can draw an axis which is the axis of temperature, and like you saw that at high temperature beyond certain point we were the collection of these molecules was a gas, but below that temperature the collection was, sorry, it should be opposite. So, no, that was right. So, the collection is gas, but below that the critical temperature you exist in a solid phase, right. But now, like I said, if you confine the particles, the very act of confining introduces the concept of pressure, and under certain conditions, and that depends upon different systems, right. So, you can introduce a new phase of matter, but you need another axis which is the pressure axis, and typically this is how the phase diagram of any material looks like, right. And this, and under certain pressure and temperature conditions you can see a liquid phase, all right. So I would like you to go home and think about this very interesting phenomenon, like liquids are not possible if you have no external pressure, right, for any material, all right. So, having said that, let us move on to kinetic theory, right. Okay, so let us move on to kinetic theory. Okay, so kinetic theory, and we can all very safely say that kinetic theory of gases, as you will see why, right. So, remember in the earlier I said that in kinetic theory we make certain drastic assumptions, right. So, let us talk about what those assumptions are, right. So, assumptions, right. So basically the first simple assumption is basically that okay, that the gas okay. So, right now I will not really say the word gas. So, okay. So, the molecules, okay, maybe I can say that. So, the gas molecules consist of point the gas molecules have no dimensions, which basically implies they are point like, right. So, they are point particles, right. And what do I mean by that? Maybe I can draw it schematically. So, say you have this collection of these molecules, right. So, you have n molecules, and every molecule has a volume small v, volume per molecule, and say V is the total volume, right. And this assumption basically just tells you that the total volume occupied by these molecules is much smaller than the total space that they are occupying, right. So, so this is what this assumption basically means. So, we are just assuming that these particles are very tiny compared to their intermolecular distance. So, that is another way to think about it, right. So, so dimensions or maybe size of particles is much smaller than intermolecular distance. Okay. So, that is like the first assumption. The second assumption is the gas molecules are moving in all directions randomly with equal probability, right. So, which means these gas molecules, they are never still, right, due to finite temperature they are always moving, and they are moving in all directions with equal probability, all right. And the one, like, now let us move on to third assumption, which is very important assumption, is so the interaction, okay. So, the potential energy, okay. So gas molecules do not interact with each other. Okay. And what that means is their potential energy is exactly 0. Okay. And if you remember, that takes us to the regime where your potential energy is much smaller than the kinetic energy, right. And or you can even see that in this case the kinetic energy will be much greater than potential energy, and therefore, like we saw, such a collection would be treated as a gas, and therefore, we are talking about kinetic theory of gases, right. So, theory that we will develop here is strictly valid only to gases which are at very high temperature, where their kinetic energy is much greater than the potential energy, and they exist in a gaseous phase, all right. Okay. And the fourth assumption is that so the gas molecules are rigid elastic spheres, right. So, molecules are rigid elastic spheres. So in coming sections, we will not really consider molecules which are oddly shaped, right. So, all these molecules are spheres and they are completely elastic, and what does that mean? If two molecules collide with each other, they will not lose any energy, right. So, basically this implies energy remains conserved after collisions, right. Okay. And you might be familiar with this when we make these assumptions to collection of these molecules. This is a gas and there is a special name to it, it is known as an ideal gas, right. So, such gases are known as ideal gases, okay, ideal gas, all right. So, let us now start doing calculations, right. So, now that we have made these assumptions, we have assumed that the potential energy term is 0, and it turns out we can now do certain calculations in a much easier manner, all right. So, let us now calculate, so let us now evaluate what is the pressure exerted by an ideal gas. All right. So, how do we start? Okay. So, say you we confine a collection of molecules in a box. Okay, so let me draw it. So, we have 3 axes. So, let us call this x, y, z, and say the gases, so the molecules. So, the molecules are contained in a cube of, okay, so let me draw a cube, and there are many gas molecules, and the length of this cube is L, which means its volume will be L cube, right. And say we have we have mu moles of ideal gas in a cube of volume L cube, right. So, that will be the volume, all right. And say these mu moles correspond to N is the total number of gas molecules, total number of molecules, all right. And let us define the number density by small n, which is nothing but total number of gas molecules divided by the total volume. So, this is number density, right. And let us assume that the mass of one molecule is m, mass of a molecule, right. And remember what we are interested in. So, we are interested in what is the pressure exerted by these molecules on the walls, right, and the container here is conveniently we have chosen it to be cubic, right. And so, like we know these molecules, they will hit this wall here and they will reflect, and as a result they will impart certain momentum, basically change in momentum onto this wall, which is create certain force, and force per unit area will be pressure, and that is exactly we are trying to solve, all right. But again remember the total number of molecules that we are dealing with is a very large number, right. So, we are talking about, for example, in this room we have anywhere like 10 raised power 26 to 10 raised power 27 gas molecules, right. So, we are dealing with very large number of these molecules, right. And since essentially what we will do is we will just statistically average out many quantities. So, for convenience what we do is, so we divide n molecules into G groups, okay. So, we are just dividing them into G groups with each group. So, each group has N1, N1, N2, so on up to Ng molecules, and all these molecules statistically they are moving with velocity v1, v2, so on up to vg, all right. So, like I said, the gases are moving with certain distribution, right, and we conveniently divide these molecules into various subgroups n1, n2, n3, so on up to ng, and every subgroup has certain velocity v1, v2, and so on up to vg, all right. And remember the G still is a very large number, right. It might be less than 10 raised power 26, but it is still very high, right. So, it's statistically a very large number, okay. Okay. So, now the reason we do this is because so basically what we can now visualize this system as follows. So, now I am just concentrating on these two walls, wall this one and this one. So, let me draw it here. Okay, so, this is, say this is the this wall A, let me call it A1, and there is another wall which is A2. Okay. And now let us look at a one molecule from group 1, right. So, since I said this molecule statistically is moving with the certain velocity v1, right, it will have 3 components. So, along x axis its component will be v1x, along y axis its component will be v1y, and along z axis its component will be v1z, right. So, what I am trying to say is that your v1 squared, which is the square of average velocity corresponding to these molecules in group 1, can be written as v1x squared plus v1y squared plus v1z squared, all right, where x, y and z are are 3 components of this velocity. Okay. So basically what will happen, right. So just imagine now let us concentrate on just one component. So for convenience let us just look at the x component, right. So what this molecule will do is its x component will move towards this wall. Okay, so let me draw it here. I am now looking at the side view, right. So this molecule starts from here, it is moving with speed v1x towards this wall a1, right. It starts from a2, it is moving here, it will make a collision here, right. So it will collide here and upon collision it will just elastically just reflect back and move back to its initial condition, right. And you can see the total distance travelled by this molecule is basically L plus L, right. So it went from A2 to A1 and again A1 to A2. So remember this length is L. So total distance is 2L, and since its average velocity is v1x, so the time taken between these two collisions, time between two collisions is basically 2L divided by v1x, right. So this is the time taken by this. And upon this collision, what will be the momentum imparted by this molecule? So remember earlier this molecule was moving with m v1x, and upon collision its momentum changed to minus of m v1x, right. So therefore upon collision, change in momentum, to be more accurate, linear momentum x component of the momentum is basically 2m v1x, right. And since this momentum is changing over a time interval which is 2L divided by v1x, so therefore the rate of change of this momentum, so rate of change of momentum is basically 2m v1x divided by time which is 2L divided by v1x, right, and this is nothing but m v1x squared divided by L, right. And this is, remember, this is for one molecule, right, for one molecule. And this is the x component, right. So, but remember in this group there are n1 number of molecules. So, therefore, total rate of change of n1 molecules will simply be n1 times m v1x squared divided by L, right. So, therefore, what is pressure? So, remember what is rate of change of momentum, that is the force, and if we divide that force by L squared, right, which is the area of the wall, that will give you the pressure, right. So, therefore, the x component of pressure okay. So, therefore, pressure on the wall which is in yz plane, on the wall or on the yz wall let us call it P1x, and this is nothing but and we can also call this as F1x, right. So, the rate of change of momentum is nothing but F1x, right. So, we can say P1x is nothing but F1x divided by the area which is L squared, right, L squared, and this is nothing but this becomes m n1 v1x squared divided by L cube, all right. So, okay. So, similarly, there will be contribution to this pressure by other groups as well, right. So, remember we are only in one group, but okay. So, by group 1. So, what will be the total pressure? So, total pressure will be sum of all these pressures due to all these groups, right. So, that will basically be P of x, which is basically just the sum over say I going to 1 to g of P I x, right, and this just becomes m by L cube of I going from 1 to g n I v I x squared, right. So, remember this this is the v, right. But remember by definition, so remember by definition, right. So, what is v 1 x squared, right. So, when I use this small v like this and in this way, they mean the same thing, all right. So, I will switch between these two. So, v 1 so basically what is the definition of v x squared average, right. V x squared average is nothing but sigma I going from 1 to g n I v I x squared divided by sigma n I, where the sigma is also going from 1 to g, right. And what is this? This is basically nothing but total number of molecules. So, this can be written as, so this is simply I going from 1 to g n I v I x squared divided by capital N. And the reason we are doing this is because we will now substitute for this quantity with n times v x squared. And what is v x squared? This is just the x component of mean squared velocity, right. Okay. So, therefore, when we do this substitution, so upon this substitution we can see that our pressure is basically just m by L cube times n v x squared average, right. All right. Now, let us now use another assumption that we made. So, remember we said that these gas molecules, they are moving in all directions with equal probability, right. So, therefore, statistically speaking, our v x squared average should be equal to v y squared average, and it should be equal to v z squared average, and also we already know v x squared average plus v y squared average plus v z squared average is nothing but v squared average, right. So, since all these quantities are same, so therefore, from these two equations we can see that the v x squared average is equal to v y squared average equal to v z squared average is nothing but v squared average divided by 3, right. So, therefore, if I substitute it here, our pressure on the yz wall, which I denote by Px, that just becomes m divided by 3 L cube times capital N times v squared average, all right. And this I will just rewrite this as follows: 1 by 3 m n v squared average, where remember n is the number density of these gas molecules, which is capital N by capital V. V is the volume of the container, which is L cube, all right. So now you might wonder that we have only calculated the pressure exerted on this wall, right. But statistically speaking, the pressure, there is nothing special about this YZ plane, right. So I could have done the same calculation on all the walls and I would have gotten the same result. So therefore, this Px indeed is basically the final pressure which is exerted by this collection of molecules on all the walls of this container, right. So therefore, I can just replace this Px with just P, which is the actual pressure that we wanted to calculate, okay. And therefore, I can write down the final result. So final result basically becomes P times V equals 1 by 3 m n V squared average, and this is the result that we have, right. So therefore, using this equation we can calculate the pressure exerted by these ideal gas molecules on the wall of the container, all right. So maybe I can write this equation in a few more ways. So say we have 1 mole of gas, right. So for 1 mole of gas, what is the number of gas molecules? That will be equal to Avogadro's number, right. So your capital N will be equal to Na, which is the Avogadro number, that will be 6.023 into 10 raised to the power 23, right. So therefore, you can write your P times V for 1 mole as 1 by 3 times m times Na times V squared average, right. So that is another way to write this, and another way to write this equation is, so remember what is m times n. So m is the mass of one molecule, n is the total number of molecules. So m times n is basically the total mass of these molecules, right. So therefore, if you divide that m times n divided by V, that will give you the mass density, right. So what I am saying is, so define rho, which is equal to m n by capital V as mass density, right. This is the mass of the gas per unit volume. So we can write our pressure as 1 by 3 rho V squared average, right. So this is the expression for the pressure exerted by a certain density of gas, which is moving with certain mean squared displacement, mean squared velocity of V squared average, right. So basically, in conclusion, what we have done is we have applied the laws of Newtonian mechanics on this huge collection of these gas molecules under the assumption that they are not interacting with each other, and they are not even colliding with each other, they are just colliding with the walls of the containers. And in this case, it turns out it is pretty straightforward to calculate the pressure exerted by such an ideal gas. And it turns out this statement is true only as long as those assumptions hold true, right. And you can already imagine, if you have a gas at very high temperature and very low density, all these assumptions are pretty much approximately true. But as long as the moment we start decreasing the temperature or start increasing the density, these assumptions, they do not hold true, and there is a breakdown of this formulation. But anyway, since this is a very elegant way of thinking about matter, which is just the collection of these gas molecules moving around, hitting the walls, giving rise to this macroscopic quantity pressure, which we can measure directly, right. So I will end this lecture here. But basically this is the whole essence of it, right. So we are in this course, we are not always interested in positions and velocities of every individual molecule, but we are interested in emerging properties of these collection of these molecules, like we just saw the pressure, right. So in the next class, we will continue with this formulation, and we will define another very useful quantity, which is known as temperature. Okay, thank you.